Okay, so let's go through a few examples here to apply some of these concepts I was talking about. The first one I want to do is number 1 on page 207. What is the angular displacement of each of the following hands of a clock in 1 hour? State your answer to 3 significant figures. So letter A is the second hand. The second hand moves 60 times around the clock in 1 hour because there are 60 minutes in 1 hour. So there are 60 revolutions that happen, and we need to convert that to radians. That'll be our angular displacement. And so we go 60 revolutions times 2 pi radians per revolutions, and our revolutions will cancel, and we get 376.8, and that will round to 377 radians as the angular displacement. But there's one thing that we need to remember about this, that is the second hand is going clockwise, and the notation with angular displacement is that counterclockwise is the positive direction, so we're going to have to report our value here as negative 377 radians. Not that. Okay, so let's take a look at one involving torque, but I guess first I have to explain a bit about what torque is. So for torque, what we're doing here is we are applying a force to an object that's able to rotate around something called an axis of rotation. So let me show you this image from our textbook right here. So this is a top view of a door. And so as we are pushing the door open, the door swings in this circular path, and my applied force is here on the doorknob, and based on the length of the lever arm, which is the distance between the force and the axis of rotation, the torque is going to vary depending on either the force or the lever arm or the angle at which I apply that force. So the equation for the torque is this. So we have the force in newtons times this whole term r sine of theta. And what that is, the r sine of theta is just a way to express the lever arm. Basically, if your force is perpendicular to the lever arm, then it's simply the force times the lever arm. So in this example, going back to here, when we're looking at this door being pushed open, let's say that lever arm the door was 2 meters wide, and my force was 3 newtons. I would just multiply those two things together, 2 meters times 3 newtons, and we would then have the torque that's being applied to cause an angular displacement. But a lot of times the direction of that force is not perpendicular, and that's why we have to deal with this r sine of theta term. And so I'm going to use this drawing I have here to explain how you approach this torque equation. So what I have here is the axis of rotation for some object that is rotating counterclockwise. And so if that's the case, our angular displacement is going to be a positive value. I have the radius of this circle as 2 meters. Now if my force were perpendicular to that radius, then that radius would just be the lever arm. But in this case, you can see the applied force here is sort of pushing out a bit. It's not tangent to that circle. So the force is going to be a little bit less. You know, the part of the force that's perpendicular to the lever arm will be what's used to calculate the force. The torque, sorry. So what we're going to do first of all is draw this thing called the line of force, or otherwise known as the line of action. And so here's my force vector coming off. This is the object right here that's going to be rotating around. This is a top view. Maybe we could imagine that this is, I don't know what it would be, something. Something that's 2 meters wide. Maybe this is a small merry-go-round, and we're not going to press tangent to the circle. We're going to sort of press out a bit, which is a little bit less efficient, and we'll see why in a second. But this line of force, you draw an imaginary line which extends beyond our actual force vector back in towards the axis of rotation until it makes a 90-degree angle with our lever arm. So basically what we're doing here is we're creating a right triangle to look at the component of the angle of this force that we're going to use to calculate the torque. So our angle that we're going to use here in this triangle that we've done is a 45-degree angle. And so the lever arm is going to be this leg of our triangle here. So we have our radius of our actual circle. And remember that if we were at 90 degrees, it would just be the force times 2. And my force here is 5 newtons, and my radius is 2. So if we applied the force like this, then it would be simple. It'd just be a 10 Newton meter torque. But since we're at an angle, only part of that force is going to be used to calculate the lever arm. And so we want to find this leg of the right triangle, which is going to be the sine of theta, so sine of 45, times the hypotenuse, which is going to be our original radius here. And so what that ends up giving me is 2, which is my hypotenuse, or the radius up here, times the sine of 45, and then I'm going to take that times 5. So going back to the torque equation, I multiplied it by the actual force. And so this whole term is to calculate the effective lever arm, is what it's called. And that's how you calculate the torque acting on an object that's going in a circular path. And like I said, that'll cause some sort of angular displacement. It might even cause an angular acceleration. And that's where we'll go probably next week. So, I think that's good. Have a good one.